Hello students, in our last video we saw some terms related to spherical mirrors or curved mirrors. We also saw that for curved mirror the focal length depends on its size. So today let's find out the focal length of a given spherical mirror. For that we'll have to do an experiment, and to do experiment we know we require raw materials. What are those? We require a concave mirror, white paper as a screen, ruler. How will you perform the experiment? Let's see it. Place a concave mirror and adjust its reflecting surface towards the sun. Place a sheet of paper, which is our screen, close to the mirror. Now direct the sunlight reflected by mirror onto the sheet of paper by moving it back and forth gradually until you find on the paper sheet a bright, sharp spot of light. Hold the mirror and screen in the same position for a few minutes. What do you observe? We observe that paper at first begins to burn. How will you come to know it is burning? Of course, there is a production of smoke. Eventually, it may even catch fire. But then why does it burn? This is because the light from the sun is converged or focused at a point as a sharp bright spot on the screen by the mirror. In fact, this spot of light is the image of sun that is formed on the sheet of paper. Why is it so small? We will see in the later videos. But for now, students imagine this so much amount of heat from the sunlight is focused at single point. Will it not burn the paper? Of course. Students, this point where the image of sun is formed, which is just a point size, is called the focus of the concave mirror. As all the rays are focused at this point, as I said, it will produce lot of heat and ignites the paper, which starts burning. Now put the ruler and measure the distance between mirror and sheet of the paper. The distance of this image on paper from the position of the mirror gives the approximate value of focal length of the mirror. Yes, students, I said approximate value. Now students, let us represent this whole experiment on a paper with the help of ray diagram. We usually do this in physics. You will also do it in your school. Students, a number of rays parallel to principal axis are falling on a concave mirror. Observe the reflected rays. They all are meeting or intersecting at a point on the principal axis of the mirror. This point is called the principal focus of the concave mirror. But how are the rays parallel to principal axis reflected by convex mirror? Because convex mirror is a diverging mirror. We know that. The reflected rays here appears to come from a point on a principal axis behind the mirror. Is it true? Yes, this is the other way of saying that the reflected rays which are diverging appear to meet behind the mirror. Thus, this is the principal focus for convex mirror. It is represented by letter capital F. The distance that we calculated between the pole and this point F is called the focal length. It is represented by small f. We know it. You know, students, these curved mirrors are made from the sphere. So the diameter of this reflecting surface is called the aperture of the spherical mirror. Don't worry, this is of importance in our later section. But you know, students, there is a relationship between radius of curvature r and focal length f for spherical mirrors of small aperture. For spherical mirrors of small apertures, the radius of curvature is found to be equal to twice the focal length. we put this as r is equal to 2f. This implies that principal focus of a spherical mirror lies midway between the pole and center of curvature. So students, we have learned how to find out focal length of a given mirror, whether it is convex or a concave. In the next video, we will see rules to represent these ray diagrams while we are representing image formation by spherical mirrors.